Very good morning to all. Today we are going to look into what is digital image processing and the first introduction to digital image processing. I'm Dr. Kavita from MIT campus. What is digital image processing? Let us see two principal areas where this digital image processing is used. Mainly, it is used in improvement of pictorial information for human interpretation and also for processing of image data for storage, transmission and representation for autonomous machine perception. Now, when I use words like a beautiful flower, a cute baby and delicious foods, these words may not be very pleasing as a visual presentation. Now, when I show you a picture of a flower, it is more pleasing than to hear the word beautiful flower. Next, a baby. Of course, delicious food like ice cream. Now, what is a digital image? A digital image, it can be defined as a two-dimensional function f of x comma y, where x and y are spatial coordinates and f is the intensity or gray level at that point. This x and y and the amplitudes of f are all finite discrete quantities, and you can see that an image is made up of finite number of elements which are nothing but the pixels, or we call it as the picture elements. Now, pixels. Now, most digital images are a grid of pixels, a checkerboard of colored squares, as you can see in the picture. As we zoom, these are the representations. These pixel is described by a number, and that is which we call it as pixel, or the picture elements, or otherwise even called as pels. Now, coming to image and its most important term, resolution. Now, the resolution of an image tells us how small and densely packed the pixels are. Now, normally we talk about resolution in terms of DPI or PPI. Now, it tells you how many pixels you have per inch. The higher the resolution, the sharper the images look to a pointer. And monitors have only 72 screen pixels per inch, that is PPI. So, any resolution above 72 won't look any sharper. Now, most web graphics have a resolution of 72 pixels per inch. Now, these are some examples of the pixels per inch. Now, this is an example of 18 ppi, 36 ppi and 72 ppi. So, we can see the difference between the three in these. Now, digital image processing and related areas. Now, we can see that we can put image processing into various levels and work upon them. Now, the first and foremost, we call it as low-level processes, where we mostly concentrate on improvement of the images, mainly for noise reduction and then for contrast enhancement. Next, mid-level processes normally involves what is called as a segmentation, where we try to partition an image or object and get the object of or the region of interest for further analysis. So, in these low-level process, which is otherwise enhancement, and in this segmentation, the inputs are images and the outputs are images or part of images. Now, there could also be mid-level processing involving classification or otherwise recognition of objects. Now, here I would like to also emphasize on what is computer vision. Computer vision, its ultimate goal is emulate human vision or high-level processes where learning, inferences, making actions, taking a sense to a set of recognized objects, perform the cognitive functions normally associated with visions, and there are no clear-cut boundaries. The origin of digital image processing, it was in early 1960s for the space program, and later after 1960s and 70s came the medical imaging, CAT, computerized axial tomography, and remote earth resources observations and astronomy. Now, applications of digital image processing. There are wide applications for digital image processing. Most commonly used application is the medical imaging, where we have the CT, ultrasound, MRI, PET, angiography based 3D reconstruction. Besides, we have remote sensing, where remote earth resource analysis is done, weather prediction, environmental assessment. For defense, automatic target recognition, image tracker, law enforcement in the form of fingerprint recognition, industries for OCR, positioning, alignment, inspection, physics, astronomy, archaeology. Now, image categorization according to the source. Image source can come from electromagnetic, acoustic, ultrasound, electron, computer generated images. So we call them as synthetic images. Now in the electromagnetic spectrum that we know, we have gamma rays, X-rays, ultraviolet, visual rays, which are normally visible to human beings, infrared, microwave, radio waves, and so on. So this is how our electromagnetic spectrum is. So images could be obtained in various bands of this spectrum. So this is an example of a gamma ray imaging. Now we can see a bone scan, a PET image, a Guinness group, gamma radiation, X-ray imaging, medical field for chest X-rays, aortic angiogram, for circuit boards, and so on. Imaging in the visible and infrared bands. So this is one typical example for infrared band based imaging. In other examples, we can see medicinal and industrial uses. In the radio band use for spine, bone analysis. Imaging in the microwave band, it's an example of a radar image of the mountains in southeast Tibet. Other modalities, we can see ultrasound based for fetal analysis. We can visualize. Other synthetic imaging modalities, example of synthetic based imaging. Now here is an example of a Landsat images from tsunami in Indonesia in the year 2004. Left you can see its natural color, and this is called as the pseudo color that is normally done to the original images in order to delineate or separate the region of interest from the background. So normally this type of pseudo coloring is done to make better interpretation from the original images. Now, so this is just a small introduction first. Now, how do we perceive information from the human eye? Now, how do we get information of an image as perceived by a human being? Now, it is through our eyes. So we have the eyes. Now, it is one of the important five senses, and this is going to be the structure of the eye, where the most important region being the optic nerves, the retina, the choroid, sclera. Now, this is the other part of the retina. Here we have the lens, the cornea, pupil, anterior cavity, and the iris. So this is the structure of our eye. Now when the eye is properly focused, light from an outside object is imaged on the retina. Now this is how we get information through our eyes. So two classes of receptors are located over the surface of the retina. One is the cones, the other is the rods. Now cones are normally 6 to 7 million in each eye, and it is the central part of the retina and highly sensitive to color. Rods, they are all over the retinal surface and sensitive to low levels of illumination. Now this is how the rods and cones are, and we have what is called as the blind spot. The image formation in the eye. Now this is how our image is as it enters to the retina. It is smaller in size and upside down. Now this is how the original image is, and we can see this is the distance. Through this distance, the focal length being 14 to 17 mm. The length of the image tree that is captured through the retina is only going to be 2.55 mm. For distant objects greater than 3 m, lens exhibits the least refractive power, and for nearby objects it shows a strong refractive. Now, some of the important terms related to perception: one is luminance, the other is illuminance, and the reflectance. It's the amount of visible light that comes to the eye, and this is illuminance is the amount of light incident on a surface, and reflectance is the proportion of incident light that is reflected from a surface. The image formation model, that is f of x, y, what we were discussing as the two-dimensional function, depends upon I, intensity component, and R, the reflectance component. Now, this is how we visualize the image, the reflective component and the illumination component. Lightness perception. Now, lightness, it's a perceived reflectance of a surface, and brightness, it is a perceived intensity of light coming from the image itself. Now, sometimes brightness is also called as a perceived luminance. This is a photography which shows the illustration of a woman. It's a standard image where we have marked A and B, which have the same lightness but different brightness. These are A and B, which have the same lightness but different brightness. This A and this B have different lightness but same brightness. So we can see that in the same image we can find same lightness and different brightness conditions. So this is about lightness constancy problem. Now, illuminance and reflected images are not arbitrary functions. They are constrained by statistical properties of the world. This is an example of having the same luminance but different or varying brightness. This is a simple example of a simultaneous contrast. You can see as the background gets lighter, the foreground small square, gets even more visible to the eye, better in intensity to the eye compared to the background. So all the inner squares have the same intensity, but they appear progressively darker over the time as the background becomes lighter. So this is called a simultaneous contrast. Now, talking about some important terms related to digital image processing. The number of pixels in the digital image is equal to number of rows into number of columns. The number of bits required to encode a pixel is called as a bit depth. It is normally in the power of 2. In grayscale, 8 bits are used to represent the shades, and so bit depth of gray level is 8. And if you use colors, set of all colors that is represented by bit depth is called as gamut. And the number of bits which are used to represent an image is normally based on this number of rows. It's normally m cross n. M is number of rows, n is number of columns, and multiplied by what is called as the bit depth. And this is the bit depth. Now, number of pixels constant, but reducing the quantization leads to what is called as false contouring. Decreasing the number of pixels while retaining the quantization levels lead to checkerboard effect, or what is called as pixelization error in an image. The pixel size is nothing but the distance between the dots. Pixel density is the number of pixels per unit length in the device monitor. Now, creating an image. Now, let us see how do we create an image. Image formation is based on the lens, which is used to gather light and focus on the image plane. Lens is characterized by focal length and aperture, and the basic length equation is given by 1 by u plus 1 by v is equal to 1 by f. So u is the distance between the image plane and the lens, and u is the distance between the object and the lens. And m is called as a ratio of the size of image to the size of the object. Now, this is how the images are digitized from a scene element. This will show us how a raster scan line is actually converted or digitized to form the pixel coordinates. This is an example of such kind. Now, image representation is normally in the form of pixels. This is a typical example of the case. And the pixel notations for the consider small region. This is how the pixels will look like for a grayscale image from 0 to 255 is the range. So, Thank you for listening to Introduction to Digital Image